Okay, guys, so we're going to be going over our force vector diagrams practice that we had done, or that I assigned yesterday. Let me share my screen with you to show you where it's at. Okay, so if you go to my physical science class, I guess I already kind of scrolled down a little bit. Uh, Go to Google Classroom and go to my physical science class. Under yesterday's quiz, you'll see the homework assignment that I had posted. Make sure you did that quiz, by the way. Vector diagrams practice. I'm going to pull up my copy of it. Actually, I'm going to make a copy of mine so that I don't mess up you guys' work. Make a copy. That way I don't mess up whatever source work you guys had in the work that you were doing. Chris says, what have I missed in the last 20 minutes? So from 9:05 until now, I gave you guys your history assignment, which you'll find on Google Classroom. Mr. Wayne reviewed an activity on evidence-based writing. Had something to do with Charlotte's Web. Premise of your first body paragraph. I think the notes should explain that pretty well to Chris, right? Yeah, Chris, you'll be able to get that from the notes. Right now, we're getting into our vector diagrams practice. And it's the same stuff we were talking about yesterday in the notes, but I wanted to give us some examples. So the first example we have is just sort of some definitions. I guess it's not an example. Um, it tells us how to find the resultant force. Remember, we add up all the forces. Okay, we'll put all the forces together. We combine all the forces. If they're going in opposite directions, of course, when we combine them, they subtract. If uh, if Joe pushes on the front of the car and I push on the back of the car, well, our forces go against each other. We're not adding our forces together to get the car unstuck, right? We both need to get on one side of the car if we want to add our forces together to unstick the car from the snowbank, like we talked about. So here we can see we've got a 25 Newton force to the left. We have a 20 Newton force to the right. This means that we're going to have a resultant force of 25, I'm sorry, of a resultant force of 5, and it's going to go to the winning side. So that's the easiest way to do it. You just subtract, the small number from the big number, and then whatever's left over, that's the amount of the resultant. And then whichever side was bigger, that's the direction of the resultant. Okay. If the total forces equal 0, then there's not an acceleration. There's not going to be a change in motion of the object. Here, the rope is being pulled on the same amount on both sides, so its motion is not going to change. It's not enough to say that it won't move because it might have been moving when they started pulling. Okay, and that's really important later on because, in a sense, this rope is on the planet Earth and the planet Earth is moving, so it is moving. What we learn here when the force is balanced is that the motion it has doesn't change. An object at rest tends to stay at rest until acted on by an unbalanced force. Here the force is balanced. Right? And an object in motion tends to stay in motion, in unchanged motion, until it's acted on by an unbalanced force. Again, balanced here. If the resultant is 0, then it is a balanced force. That's Newton's first law. Here, though, we have all the forces acting on one side. And so there's nothing to subtract. The green team's not here anymore. Um, to find the resultant here, it's just going to be 20, that's not 20, 20 plus 20 plus 15 plus 30. So our result is going to be 85 newtons. And it's going to be 85 newtons to the left. I'll just write left because that arrow is kind of small. 85 newtons to the left. Does anyone have any questions about how I found the resultant force here? Forces were all acting in the same direction. Because they were acting in the same direction, they get added together. Here's another example. I have 20 newtons plus 20 newtons plus 10 newtons plus 35 newtons. I add those together, again, I get 85 newtons. Is it the same force that we had before? Tell me in the chat, is that the same force that we had before? Is the green team's force the same force as the blue team's force that we did before? Ryan says yes. Someone else give me an answer here. Veronica says yeah. Trevor says yeah. So here's the thing. It's the same amount of force, but it's not the same force. And here's why. Look, the blue team is pulling to the left. The green team is pulling to the right. So they're not actually the same force. They have the same magnitude, the same amount of force, but they're going in opposite directions. So they subtract from each other. They're opposite forces, okay? And when they're opposite, they subtract. That's the point that we were trying to get from these examples here. Does that make sense? Mr. Wayne pulls that way and I pull this way. Our forces subtract from each other, okay? Or if he pushes this way and I push that way, same thing. Pushes and pulls are, in physics, are very much the same thing. Okay, now here we've got another question. It's a little more complicated, but at the same time, it's a little simpler. There are less terms to add here. What is the resultant force? So the first thing we should notice here is that these forces are opposite. And because they're opposite, what are they going to do? I'm looking for some feedback here, guys. Because the forces are opposite, what should we expect them to do? Subtract. Thank you, Ryan. Guys, I need you guys to hop on this like Ryan did. Yeah. The forces are acting in opposite directions. Because they're acting in opposite directions, they subtract. Okay. So here's what that's going to look like. It's going to be 2200 minus 2500. I don't like that because we know that's going to give me a negative number, right? There's not a negative amount of force unless you consider to the left negative, or sorry, to the right negative. The better way to look at this would be 2500 newtons of force minus, that's an equal sign, minus 2200. And this is going to give me 300 newtons of leftover force. But our resultant force has a direction. In which direction does it go? The direction of the resultant force goes to the winning side, the side that has the greater amount of force. In this case, to the right with green team. Is that what you guys put? All right, full disclosure here. Tell me in the chat if you did not do this homework. I'm not going to write you up or anything, but I do expect you guys to do it. Just tell me if you didn't do the homework. Here we have another problem. It's really just like this, it's exactly like the last one, just with different amounts. If I have a 400 Newton force this way, and 200 Newton force this way, I know that it's going to be 400 minus 200. Okay? 400 newtons minus 200 newtons. And then I'm going to have 200 newtons left over. Michaela, what's your question? You can say it in the chat, or you can say it out loud if you want.
By the way, if anyone ever wants to ask a question and doesn't want the rest of your classmates to see it, you can always at the bottom of the chat click that arrow and pick either myself or Mr. Van Wy, and send the chat directly to us. So it'll be a private message. That way you don't have to worry about asking a question that you feel might make you look bad. I don't know. I don't. You shouldn't feel bad asking a question, but if you do, then you can always just send a private message to us too.
Michaela says, was this on the Google Classroom? Because I just studied in the paper that we did. Yeah, I'll show you right where it was. It's actually where we started. Go back to physical science here. Okay, you go down. I like to go right to the classwork tab. It was on the screen, but it's easier to find in the classwork tab. Now to Unit 3, Forces and Diagrams. We had the quiz that you guys were assigned yesterday. And here you have Vector Diagrams Practice. I should probably change the label of that and call it 3.2. Sorry about that. Okay. Yeah, Vector Diagrams Practice. And that's what we're in the middle of right here. Okay. So here we've got 400 newtons to the left, minus 200 newtons to the right. So if I have 400 left minus 200 to the right, then don't be sorry, just do it next time or do it later, because I want you guys to have the practice so you guys will do well on the quizzes and stuff. You not doing your homework does not hurt me. It does hurt you. So that's what I want. I want you guys to do well. So 400 minus 200 gives us 200 newtons, and the winning team is to the left. So whenever we're finding resultant forces, guys, remember our rule is find the difference in forces, okay? Subtract them to find out how much difference there is. And then whichever team pulled or pushed harder, that team wins. That side wins. I hope that's clear. I would ask you guys if that's clear, but 2 of you would answer and the rest of you would not. Yeah, I don't know. Here, it's asking what is the resultant force below? Well, I'm going to spoil it. This blue team and this green team, it's the same one as up here when we were doing these. It's the same amounts. So it's 85 on this side. It's 85 on this side. So it's going to be 85 minus 85. 85 minus 85 is 0, so it's 0 newtons. In which direction does 0 newtons of force act in? None. No direction. A resultant of 0 does not have a direction. Okay. Now, we're getting into vector diagrams. This is the stuff we started to talk about yesterday. Forces can be shown using arrows. They're actually not arrows, they're vectors. But a vector looks an awful lot like an arrow to you guys. The dot here, this area, where's my spotlight? The dot, that shows us where the force is applied. Okay. Now we'll talk more about this later when we get into free body diagrams, but it shows us where the force is applied. Okay. The point, of course, shows us the direction of the arrow. I know this seems obvious, but it's worth saying out loud in case anyone's confused. The point shows us the direction that the force acts. And then the length of the vector shows the amount of force. So the longer this arrow is, the more force it's showing. Okay. And that'll always be true until we start just labeling the amount of force when we draw our vectors. But technically, we should always make the length of the arrows proportional to the amount of force. Again, we'll see what this kind of looks like when we do free body diagrams. There are some shortcuts to this. So we're not drawing forces that go clear off the page, or vectors that go clear off the page. Each square in the vector diagram, remember, represents 1 Newton of force, although I could say that each square represents 1,000 newtons of force if I wanted to. Okay. The grid is just here to show us the length of the arrow. Okay. We could do all of this without the grid. It still is the same length of arrow. Okay. The grid just helps us measure the length of the arrow. But when we measure, remember to count the number of squares that the vector covers, not the number of lines that it passes. Okay. That just helps us on our practice work. This vector shows us a 5 Newton force to the right. It's acting right here, and it goes in this direction with 5 newtons of amount or magnitude. So this is the whole reason we're getting into this activity. We're going to take and resize this arrow to show a 5 Newton force to the left. Okay. So we'll leave it acting right here, and right now it's covering 1, 2 squares. So I grab the end of this, and I go 1, 2, 3 more. And I look, does it cover 5 squares? 1, 2, 3, 4, 5 squares. Boom. This is what your practice work should have been. Again, if you guys haven't done this yet, you can go back and fix and do your practice on your slides. Everyone has their own copy of this. Okay, this says resize the black arrow to show a force of 3 newtons down. So here's 1 Newton down. I need to move some things around here. 1 Newton down. 2, 3. 1, 2, 3 squares that it covers. Okay. So now we're drawing force vectors. When we were doing this on paper inside of class, this all made a lot more sense. It was a lot, we were able to get a lot more practice on it. But hopefully you see that the length of the arrow tells us how much force we're talking about. That's the whole point here. Yeah, but I can't draw straight in MS Paint. Well, I guess there are line tools there. Yeah. The slides is nice because it lets me separate out each problem on its own slide. Oh yeah, it would have been a nightmare. Doing any of this with Windows 95 would have been a nightmare. Okay. So remember back before, like 5 or 8 slides ago, when the forces act in the same direction, way up here on slide 4, when forces act in the same direction, they add together. Well, that's true down here with vector diagrams as well. Okay. Forces can act in different objects at the same time. When they do, the forces can be combined. Inside of our physical science class, we're only going to talk about forces that act in line with each other. Okay? We're not going to talk about forces that act either off angle from each other or otherwise not parallel. In a physical science class, we're only going to talk about parallel forces. Okay? The forces that act on the same plane, the same line. In a physics class, you can have, one force acting on the right side of a box and another force acting on the left side of the box. It's going to cause the box to spin, something like that. But we're not going to do that here. We're not. Okay? We're not in a physics class. This is physical science. Anyway, these forces, because they act in the same direction, they get added together. Okay? Here I have a 1, 2, 3 Newton force, and I have a 1, 2 Newton force. They add together. That gives me 5 newtons to the left. They're both acting on the left. Here, the forces are acting in opposite directions. And here I colored them, the red to the right, blue to the left, just to make it easier for us to kind of see that. But this is a tug of war now, or an arm wrestling contest. When they act in opposite directions, the force of the smaller one takes away some of the force of the larger one. That's kind of the way to think of it. In other words, you subtract, and the winner of the contest gets the direction of the force. So here I have 1, 2, 3, 4, 5 newtons to the right, and I have 1, 2 newtons to the left. My resultant force is going to be 3 newtons to the right. Just like when we had the tug of wars up above. Now, we can draw a resultant vector. This should have really been black, I guess. We can draw a resultant vector to show the resultant force. We can draw our own arrow to show the amount of force that's left over. Do that below. It says move and resize the arrow below to show the resultant vector. So let's think. I've got 1, 2, 3. To the left, I've got 1, 2, 3, 4, 5 to the right. So let me do some math here. 5 minus 3. That's 2 newtons. Okay. And I know that it's easy enough to subtract 5 minus 3 without typing it out, but I wanted to show you guys my thought process here. So I've got 2 newtons, and which arrow is longer? The arrow to the right. Okay. So it's going to be 2 newtons to the right. So then when I draw my resultant vector, I just need to go in here. I want to put him right there. Oh, that's not what I meant to do. It's okay. Grab this. I'll put it right here. And I've got 1, 2 newtons. Bam, 2 newtons. That's my resultant vector. Okay. Does everyone feel like you can draw a resultant vector now? I hope so. I hope so. I feel like these are decent examples.
I see one yes in the chat.
Michaela says kind of, so that's good. Let's do another example. Okay. It says move and resize the black arrow below to show the resultant vector. Well, let's do some math first, okay? Over here. So let's think. I've got 1, 2, 3, 4, 5 newtons up. Write that down here. 5 minus. They're going in opposite directions. So because they're going in opposite directions, I know that they need to subtract. Okay, so 5 minus 1, 2, 3. 5 minus 3 gives us 2 newtons. And which side wins, up or down? What do you think, Mr. Wayne? Which side wins?
Up.
Up. The blue arrow is longer. The up arrow is longer. So it wins. So I'm going to drag my force vector over here.
Is that kind of like when I have one of those helium balloons and they don't put a big enough weight on the bottom of it so it goes up anyway?
That'd be a good example of this, yeah. Actually, with these amounts of forces, that's about right. Helium balloon, a big enough helium balloon, it can give you about 2 newtons of force up as the resultant vector. Well, 5 newtons up, but your little weight only gives you 2 newtons down or 3 newtons down. You end up with a 2 Newton resultant force upwards. So the balloon accelerates upwards. Okay. This red arrow shows the force of gravity acting on the balloon. The blue arrow shows the force of buoyancy, which is a force we didn't really talk about, acting on the balloon in the up direction. Well, if the buoyancy force is bigger than the gravity force, then the thing flies up in the air. It literally floats on the air, just like a balloon full of air would float on water. Okay. The resultant force. Okay, we're doing this again. Got 1, 2, 3, 4 newtons up. I've got 1, 2, 3 newtons down. That gives me 1 Newton. And which side's bigger, the down or the up? Yeah, the up. So I'm going to take, I keep grabbing the wrong part of this arrow. There you go. You'll notice I'm okay just drawing my resultant vector right next to my vector. It's only See, technically this point should act in the same space as the blue one or the red one here. There's just not room to show that on the diagram. So we're drawing it next to it. And we know that we're kind of cheating by doing that. But there's just not room. There's not even room to draw a 1 Newton vector here.
You know why female ants always sink?
Mr. Wayne asks, do you know why female ants always sink? No, why do female ants always sink?
Because they're not boy ants.
Because they're not boy ant. Moving on. Okay, we got one more here. So I have a 1, 2, 3 newtons up. I have a 1, 2, 3 newtons down. So my math looks like this. It is 3 minus 3. That resultant is going to be 0 newtons. So where do I put this arrow now? Which way does it go? It doesn't. There's no resultant vector. There's no vector to draw here. You just delete it. It doesn't belong. Stays over here off of our grid because it's not a vector that would exist. Okay? There's no resultant force there. And of course, we remember from Newton's first law, okay? Where'd it go? F equals ma. Also A equals F over M. Okay. So if A equals, you have to forgive the uppercase A. This thing keeps auto-correcting me. A equals, if the F equals 0 here, if the resultant force is 0, acceleration equals 0 over the mass. Do we even need to know what the mass is? Let's say the mass is 2,500, right? What's 0 divided by 2,500? 0. The acceleration of an object where the forces balance each other, the mass doesn't matter. If the forces balance, then the object does not accelerate. That's Newton's first law of motion. Okay. It's actually Newton's second law of motion as well, because it says that the amount of force on a mass tells you its acceleration. There's no resultant force. There's no acceleration. All right. You guys see how our last unit over Newton's laws, how it applies when we start drawing these force vectors, and how we're really just getting into more of the same stuff. I hope that you guys will continue to see how we will go from talking about Newton's laws to forces and force diagrams to now the next thing we'll be getting into is talking about acceleration and how much something accelerates and what that depends on. So all of these ideas go together. The final slide talks about the math that we won't do, okay? If I have a force of, what is this, 1, 2, 3.5 newtons, because it's more than 3, because it's 3 up and 2 over, and I add that to 1, 2, 3 down, then I'm going to end up with a vector that kind of goes like this. Okay, that's vaguely what it's going to do. It might even go this way. But we're not going to do that math. We're just not going to. When we combine these two amounts, we can't just subtract. We have to take the square root of the sum of their squares, or a squared plus b squared equals c squared. That's trigonometry. We're not doing that. You guys don't have that trigonometry yet. You guys you may have those skills, but they're just not things that we even talk about in a physical science class, as we were saying before. We just need to know that forces can act on objects in all different directions at the same time, and the forces, they get combined together. The forces that are in a line together either get added together or subtracted from each other, depending on which direction they go. They go in opposite directions, they subtract. They go in the same direction, then they add. Okay. If anyone has any questions, I will keep this. We will keep this Zoom meeting going. I think Mr. Wayne still has some more. Yeah, Mr. Wayne's done. I'm done with science. Make sure that, what is today's science? Oh yeah, make sure you do your quizzes, guys. We have a couple of quizzes today. We have a science quiz over the vocab, the quiz that I was supposed to get you guys yesterday, and we have our history quiz over the textbook stuff that we did yesterday. Okay. If anyone needs anything at all, we're going to stay on this Zoom chat for almost another hour here. This was kind of a quick day, but you guys have plenty to do. So thanks a lot, and we'll see you next time. 9 o'clock.
Remember, we're done early today, so you'll have time to get work done. See you guys later.
Yeah, not so that you can just chill.